Hi everyone, my name is Hao He. I'm a third-year PhD student working at McMaster University. Today, I'm working with Dr. Christine Wilson. Today, I'm going to talk about one of my projects on young massive star clusters in the antenna merger. So, as we all know, stars are generally formed in the molecular gas. And the molecular gas is generally exists in the form of the giant molecular clouds. And since we know that typical giant molecular clouds have a gas mass of 10 to 6 solar mass, so there are lots of stars. There should be lots of stars formed in GMCs. So typically, we would expect stars formed in star clusters, and there are lots of such systems found in Milky Way inside the GMCs. So we call that young massive star clusters or YMCs. So a typical YMC defined in the Milky Way has a mass greater than 10 to the 4 solar mass and age smaller than 500 megayears. So people have also looked at the galaxies outside the Milky Way and see if they can find like such system in the other galaxies. And actually, they have found lots of those systems in other galaxies, specifically in starburst systems. And the left plot shows one of the observations by ALMA 2021. And we can see if the star cluster, the surface density of the star formation increase, more and more stars will be formed in clusters. Like it can reach to like 80%. So basically for starburst systems, we are more easy to find those young massive star clusters. And the right plot shows work done by MOC 2020, and basically it shows the mass function for GMCs and YMCs. And we can see that for starburst systems such as Antennae and the NGC4038, the mass function is extend to high values of 10 to the 6 solar mass. Therefore, we can say that for starburst systems, they are not only likely to form young massive star clusters, but also the YMCs has higher mass for those systems. And that's the motive for us to study the YMCs in the antenna. So the other name for the antenna is the star cluster factory. We can easily see that from the left plot. As we can see, the cluster mass function for the antenna is higher than the rest of other galaxies. So, and also it extends to high mass range, which is greater than 10 to the 6 solar mass. Also, people have found a lot of young clusters in this system. And if we want to look into some extremely young clusters, which actually just trace the star formation activities that are ongoing in this system, then we should better look at those YMCs in radio wavelengths, and because these young YMCs should be in cloud still, and there's lots of gas in the cloud, and in this case there will be a lot of extinction, and we might not be able to see that in optical wavelengths. So here I show the ALMA data for the antenna merger at both GMC scale and the YMC scale. So the typical GMC scale is 60 parsecs, and the typical YMC scale is about 10 parsecs. So for those two images, it shows emission 100 gigahertz continuum emission, and we can see like by comparing these two maps at different scales, we can see the GMC sources corresponds to YMC sources quite well. And the 100 gigahertz continuum generally treats the free emission from these systems. We also have the 220 gigahertz map at the GMC scale and the 345 gigahertz map at YMC scale. You can also see a good correspondence between these two maps. And for those emission at higher frequency, it also got like dust components. So therefore, by subtracting the free emission, and we can calculate the dust emission and use that to trace the dust properties and gas properties in these systems. So here is a summary of our data. So basically, we have 100 gigahertz continuum, which traces free emission. And based on some assumption on IMF and the stellar population, we can calculate the stellar mass. And we also, so basically the red plot shows one of the SED fitting for one star clusters in one dwarf galaxy called Henius 210. So we can see from this plot, like the 100 gigahertz continuum corresponds with the free emission, and which can do those things. And we can also calculate the dust emission. I think based on like a 345 gigahertz continuum here. And if we can calculate the dust emission, we can then calculate the dust mass by assuming a certain opacity and dust temperature. And under like assumption of a certain gas to dust ratio, we can calculate the gas mass. We also have the CO 2:1 maps at both GMC scale and YMC scale, and directly we can calculate the velocity dispersion in these systems, which kind of let us know the dynamical state. And also, if we assume like an LTE assumption, we can actually use that to calculate the CO gas temperature, and therefore we can assume dust temperature is equal to the gas temperature, and hence calculate the dust mass based on that. So before we dive into those radio data, the first thing we can do is to compare the radio emission with some optical maps to see like if they are well correspond with each other. So here we choose the Paschen beta emission because Paschen beta emission actually traces the emission from the ionized gas. And it's also true for the radio free emission at 100 gigahertz continuum. So we can compare these two maps to see if they give us like a consistent results about like source properties. And in the left plot, it shows the Paschen beta map and the zoom in for individual sources, and the pink contour is basically the 100 gigahertz continuum, and the red contour is 345 gigahertz continuum. We can see that most radio sources have their companion Paschen beta source, and which means maybe like they are tracing the same source. The two emissions are tracing the same source, but on the other hand, there are some offsets, and in the upper right plot, we plot the offsets between the Paschen beta emission and the radio emission. And we can see the offsets distribution is kind of random, and it's all about like 0.1 arcsecond. So it seems those offsets should be real rather than astrometry calibration error. We also plot so since both Paschen beta emission and radio emission trace the ionized gas, we can use both emission to calculate the total ionizing photon number. And in the lower right plot, we show the comparison for this quantity between those two emissions, and we can see basically they agree quite well. So that kind of tells us that they should come from the same physical source, but also they have some offsets, so there's some controversy about that. And our explanation about that is as we think like maybe this clusters, it lives in the edge of the cloud, and it actually poked the hole in outside the cloud. So there's some ionized photon leaked out, which we can observe by observe at the like Paschen beta wavelengths. And also for the radio free emission, we can observe that for the ionized region inside the cloud. So we kind of see the slightly different parts of this system, but since they are kind of just one system, we expect the photon number traced by those two emissions are comparable with each other. Okay, so now we can dive into like our analysis on like individual sources. So in the right plot, we show like zoom in image for different sources. The left column is at a GMC scale, and the right column is at YMC scale. So basically for easy comparison, you can basically the red cap aperture at the middle column is the same aperture as the left column. So we can see actually the YMC source is quite compact compared to the GMC source. And in the right column, it shows the maximum resolution we can get for 100 gigahertz continuum. And we can see that for our highest resolution map, even some sources are broken into two sources. So it means like we can resolve it with higher resolution data. So the right spectrum is from the CO spectrum measured at both GMC scale and YMC scale. And from that, we can actually calculate the velocity dispersion. So since we have the velocity dispersion and the radius, we can calculate the visual mass of those systems. And we also know the stellar mass and the gas mass based on the free emission and the dust emission. So we can calculate the total mass of the system and compare that with the virial mass. And we can see that for most star clusters, they are bound systems with a total mass greater than the virial mass. So another thing we can do is, since we have the radio emission at both GMC scale and YMC scale, we can compare the fluxes from those two scales, which is shown in the left plot. And basically, we can see like for free emission, it's kind of concentrated in those small, tiny YMC systems. But for dust emission, the distribution is more extended. And the YMC dust flux only takes up about like 20% of the GMC flux. So this suggests that most of the stars formed in those GMC systems actually is being formed in those YMC systems. And specifically for free emission, this ratio can tell us the cluster formation efficiency or bound fraction, which tells you how much fraction of the stars actually formed in clusters. And we can see that basically there's about 50% of the stars formed in clusters in the antennae, and it's kind of correspond well with the theoretical prediction by Orson 2012. Another relation we can test is YMC versus GMC mass correlation, which is found by Howard 2018. And so the left plot shows the stellar mass of the YMC versus GMC mass, and the right plot shows the total mass of the YMC versus GMC mass. From both maps, we can see that there's a good correlation between the GMC mass and the YMC mass, which is kind of generally agrees well with the simulation prediction. And it's specifically like for some sources, like for this source that is lie below the simulation prediction, actually this source, we think this source is forming stars, and there should be more stars to form. So if we use total mass, it brings this point up closer to the correlation. And on the other hand, for some Milky Way sources, we can see it lies above the correlation, but basically the YMC is far from the matched GMC cloud. In this case, we think actually those YMCs have destroyed part of the GMC cloud. So therefore, the GMC mass is lower than what we expect. I will leave my summary here, and I'm welcome to any questions. Thank you.